Hello and welcome to all students. In this lecture, we learn about Hausdorff property. Hausdorff property. So, let us state the theorem based on this property. Uh, and this Hausdorff property or theorem says that any two distinct real numbers have disjoint neighborhood. Any two distinct real numbers have disjoint neighborhoods. That is, if x, y belongs to R and x, y they are not same, then there exist real numbers R1 and R2 such that neighborhood of x with radius R1 and neighborhood of y with radius R2 have no common point, means their intersection is empty, where neighborhood of x with radius R1 is a neighborhood of x with radius R1 and n of y R2 is the neighborhood of y of radius R2. Let us write the proof of this theorem. So how we will prove this theorem, that is very important now. So we have to show the intersection of these two neighborhoods is empty, and let us assume that there is a one real number in the intersection and reach to the some contradiction. So let x comma y belongs to R, means x and y are real numbers and they are not same. Therefore, their modulus, their subtraction is not equal to 0 and therefore their modulus is not equal to 0. And let alpha is equal to mod of x minus y, means alpha is a positive quantity, non-negative quantity. Now we claim that the neighborhood of x with radius r1 intersection with neighborhood of y with respect with radius r2 is empty. This is our claim, and we suppose there is one element in between the intersection, means a belongs to the intersection of neighborhood of x and neighborhood of y with radius r1 and r2 respectively. Then as a belongs to the intersection of these two neighborhoods, therefore a will be in each of these two neighborhoods. Therefore a belongs to neighborhood of x with radius r1 and a belongs to the neighborhood of y with radius r2. Therefore, what happens if a is in the neighborhood of x with radius r1, then the distance between x and a is strictly less than r1, and as a is in the neighborhood of y with radius r2, then the distance between a and y is also strictly less than r2. Therefore, mod of x minus a is less than r1 and mod of a minus y is less than r2. Now, so all these inequalities we have to keep in mind. We will use afterwards. Now consider the mod of x minus y, and it is equal to, we make some adjustment, mod of x minus a plus a minus y, and we separate the modulus by triangle inequality. It is less than or equal to mod of x minus a plus mod of a minus y. But mod of x minus a is strictly less than r1 and mod of a minus y is strictly less than r2. Therefore, this inequality, the second step is strictly less than r1 plus r2. But r1 and r2, they are same. R1 and R2 they are same because we are choosing R1 is equal to R2 is equal to mod of x minus y divided by 2, means alpha by 2. Okay, so 2 times alpha by 2 is alpha. Therefore, mod of x minus y is less than or equal to, therefore mod of x minus y is strictly less than alpha. And finally, this gives mod of x minus y is strictly less than mod of x minus y. And this is impossible inequality because one real number will be never will be strictly less than itself. Therefore, the intersection of these two neighborhoods is empty. So this is the end of this proof. This is the end of Hausdorff property or Hausdorff theorem. Now let us go to the next point, and that point is bounded sets of real numbers. Bounded sets of real numbers. Now let us we define what is meant by upper bound. What is meant by upper bound? A subset S of R is said to be bounded above. Is said to be bounded above. A subset S of R is said to be bounded above if there exists a real number U such that X is less equal U for all X belongs to S. The meaning of this definition is that a subset S of set of real number R, a subset S of real number R, a subset S of a real numbers R is said to be bounded if there exists a real number U such that all elements of set S they are less equal the real number U. So this is simple and it is true for all S. This is true for all X belongs to S. And in that case, the real number U is called an upper bound of S. Okay, upper bound of the set S. So this is the definition of upper bound of a set. Now, what is lower bound of a set? Similarly, we define here a subset S of set of real number R is said to be bounded below if there exists a real number L such that all elements of set S are greater than or equal to L. Means X is greater or equal L for all X belongs to S. And in this case, the real number L is called an lower bound of the set S. Lower bound of set S means set is bounded below. Set is bounded below. If lower bound exists, then we say that set is bounded below. If upper bound exists, then we say that set is bounded above. So if lower bound exists, then what happens? All elements of set S they are greater or equal lower bound. And if upper bound exists, then all elements of set S they are less equal that upper bound U. If a subset S of R is both bounded above and bounded below, then such a set is called as bounded set. So when we say a subset of a real number R is bounded, if that subset S has lower bound as well as upper bound. Now let us see one theorem on the bounded sets. Let capital S be a bounded subset of R. Let capital S be a bounded subset of R. Then there exists M belongs to R plus. Means there exists a positive real number M such that mod of X is less equal M for all X belongs to S. Let capital S be a bounded subset of R. Then there exists a positive real number M such that mod of X is less equal M, and it is true for all X belongs to S. Means if set is bounded, then mod of all elements of set S if they are less equal some positive real number M. So let us try to prove this theorem now. Let S be a bounded subset of R. This is given to you. Therefore, there exists a lower bound and upper bound. There exists L and R belongs to R such that X is greater equal L and X is less equal U for all X belongs to S. L is the lower bound of set S and U is upper bound of set S. Let capital M is equal to maximum of mod L and maximum of mod L and mod U. Capital M is equal to maximum of mod L and mod U. Therefore, capital M is greater equal mod L, but mod L is greater equal minus L. Since mod L is maximum of L and minus L, that thing is known to us. And mod M is greater equal mod U greater equal U. Therefore, M is greater equal minus L and minus M is less equal L. If we change the sign, inequality will get changed. Now finally, now what we have is X greater equal L, X less equal U, but L is greater equal minus M and U is less equal M for all X belongs to S, and this implies that X is greater equal minus M less equal M for all X belongs to S, and finally we have mod X is less equal M for all X belongs to S. So the this is the proof of this theorem. Okay, so let us stop here. Thank you very much.